Hey there and welcome. So, have you ever poured hours, maybe even weeks, into a machine learning project only for it to go absolutely nowhere? If you have, trust me, you are not alone. Today, we're going to skip the hype and build the actual roadmap that separates those failed projects from professional, repeatable success. Let's dive in.
It's a pretty shocking number, isn't it? 90%. All these brilliant ideas and ambitious projects just fizzle out. But what if I told you the reason they fail isn't what most people think it is? You know, a lot of beginners get obsessed with finding the most powerful, the most complex algorithm they can. They think they need a massive neural network or some super fancy new technique. But honestly, that is almost never the real problem.
The real culprit, the silent killer of ML projects, is a lack of process. Success here isn't about just throwing a powerful model at a problem and hoping for the best. It's about a disciplined, systematic, repeatable workflow. And today, we're going to walk through that exact process, step by step.
So here's our game plan. We'll start by looking at why so many projects fail. Then we'll get a handle on our basic tools. And after that, we'll master the 7-step professional workflow. Then we're going to get into the really good stuff, the bias-variance trade-off. Finally, we'll see it all in action and wrap up with the key things you need to remember.
So, what is this great failure I'm talking about? Well, it's that temptation to just skip all the boring prep work. You get your hands on a data set, and the first instinct for so many of us is to just plug it straight into a model and hit run. But that approach, it's a recipe for disaster. It completely ignores the careful, structured thinking you need to build a model that actually works in the real world. Okay, so before we can start building, we need to know what's in our toolbox. And broadly speaking, machine learning pretty much falls into 3 main categories. Figuring out which one to use all starts with understanding the kind of problem you're trying to solve.
So, supervised learning is the one you'll see most often. It's kind of like teaching a student with a textbook that already has all the answers in the back. Then you have unsupervised learning. That's more like detective work. You're sifting through data without any labels, looking for hidden clues and patterns. And finally, there's reinforcement learning. Think of it like training a dog with treats. An agent learns by trial and error, getting rewarded for good decisions and penalized for bad ones. All right, here we go. This is the absolute core of our explainer today. This is the blueprint that professionals follow, and it doesn't matter what problem they're solving or what algorithm they're using. It is a strict sequential process that guarantees you're building something solid.
Let's just quickly run through this. It all begins with data collection. Pretty obvious. You got to get the raw info. Next, and this is super important, is pre-processing. This is where we clean up all the mess, handle missing values, and just get the data ready. After that, we get creative with feature engineering, where we might cook up new variables to give our model better clues to work with. And only then do we get the splitting data. From there, it's on to training the model, followed by a tough evaluation to see how it performs on data it's never seen. And finally, if it makes the cut, it's ready for deployment. Now, every single one of these steps is crucial, but today, let's zoom in on the one that trips up beginners more than any other. This is it. This is probably the single most important rule to prevent your model from cheating. We always, and I mean always, have to hold back a piece of our data, usually around 20%, that the model never, ever gets to see while it's learning. This data is the final exam.
And this analogy just nails it. A model that gets to see the test data ahead of time isn't actually learning anything. It's just memorizing. It'll look like a genius on the data it's seen, but the moment you give it something new, it will be completely useless. We call this data leakage, and it's a cardinal sin in machine learning. Seriously, avoiding this mistake is non-negotiable. It's the foundation of building any model you can actually trust. But once we have that foundation in place, we can move on to the next level, really understanding and fine-tuning how our model performs. Okay, now that we have the workflow down, let's get into the concept that truly separates the amateurs from the experts. If you can wrap your head around the bias-variance trade-off, you unlock the key to fine-tuning a model and getting the best possible performance. So, what is bias? Well, you can think of bias as the error you get when your model is just too simple. Imagine trying to predict the crazy ups and downs of the stock market using just a single straight line. Your model is way too basic to capture the complex reality of the data. This is what we call underfitting. Variance, on the other hand, is the exact opposite problem. This is the error you get from a model that's too complex, too sensitive. It doesn't just learn the real pattern in your data,
It starts memorizing every little random quirk and bit of noise, and we call this overfitting.
This slide here just lays out the two problems perfectly. On the left, with underfitting, your model is just consistently wrong. It's pretty easy to spot. But the one on the right, overfitting, that one's much more dangerous. Why? Because it looks like a genius on your training data. It gives you this false sense of confidence, but then it completely falls apart the second it sees new data from the real world.
Let's go back to our student analogy. A high bias model? That's like a student who didn't study at all. They're going to fail everything. But a high variance model, that's the student who memorized every single word of the textbook, but has zero real understanding. They can recite a chapter perfectly, but ask them a question that requires just a little bit of critical thinking, and they are totally lost.
So how do you diagnose this stuff in the real world? It's actually pretty simple. You use this table. If both your training and your testing errors are high, your model is too simple. It's underfitting. If your training error is super low but your testing error is high, your model is too complex. It's overfitting. And that sweet spot, the good fit, is when both of your errors are low and pretty close to each other.
Okay, that was a lot of theory. Let's make this really concrete with a quick, real-world example. Let's see how all these ideas play out if we were trying to predict house prices.
So imagine we try to predict a house's price, but we only give our model one piece of information to work with, the size in square feet. This is a textbook case of high bias, or underfitting. The model is just way too simple. It's totally ignoring these hugely important things like, the neighborhood, or the number of bedrooms, or how old the house is. The fix is pretty obvious, right? We have to give our model more information, more features, so it can capture the true complexity of the housing market.
All right, we have covered a ton of ground today, everything from the high-level workflow to the tiny details of model performance. Let's boil it all down to the 3 core ideas that you absolutely need to take away from this.
So here's what you need to burn into your brain. First, master the workflow. A disciplined process will beat a fancy algorithm any day of the week. Second, treat the train-test split as your golden rule. It's your only real defense against a model that's lying to you. And finally, remember that the whole game is about balance. You're always on a quest to find that perfect sweet spot between a model that's too simple and one that's too complex.
And that's it. You now have the framework that guides pretty much every successful machine learning project on the planet. These concepts, the strict workflow and the bias-variance trade-off, they aren't just abstract theory. They are the practical, everyday tools of the trade. So the only question left is, what are you going to build with them?